Hello, and welcome to this episode of Every Current. I'm your host, Bill Florence, and today I'm joined by two very distinguished guests, John Bistline and Jesse Jenkins, who are here to discuss the energy impacts from one of the most significant pieces of federal legislation passed in decades, the Inflation Reduction Act, or IRA. John, let's begin with you. Could you just provide a quick overview and introduction of yourself, please?
Sure. I'm John Bistline. I'm with EPRI's Energy Systems and Climate Analysis Group. I'm a program manager and lead our energy, environmental, and climate policy analysis research. Also one of our lead developers of our regen model, which we use to investigate energy systems planning and policy questions, including looking at the impacts of the Inflation Reduction Act.
Jesse, would you introduce yourself, please?
Hey, everyone. I'm Jesse Jenkins. I'm an assistant professor at Princeton University, where I have a joint appointment at our Andlinger Center for Energy and the Environment and the Mechanical and Aerospace Engineering Department. And I run a group called the Zero Lab that specializes in building macro-scale energy system models, so the kinds of tools that John was just talking about to model the evolution of energy systems, the impact of novel technologies, and provide guidance on for innovators and investors and technology developers today about how they can improve the chances of having significant impact for those technologies over time, and evaluation of policy and planning decisions so that we can help provide decision support that can accelerate the energy transition.
That sounds fascinating. Let's jump right into this. Most people may be familiar with the Inflation Reduction Act, or IRA, but let's just, for those maybe who need a little refresher, can we just do a little high level introduction to the act, and maybe specifically focus on some of the power sector focused elements of the IRA?
Sure. You can think of the IRA as an all-you-can-eat buffet of decarbonization incentives. It gives several tax credits for clean energy deployment, ones for electrification, methane reductions, promoting domestic supply chains, as well as addressing environmental justice, among other sort of non-energy and climate provisions. But our analysis and others suggest that the tax credits for zero-emitting electricity generation, for things like wind, solar, and others, those are large potential drivers of emissions reductions from IRA. Those extend existing credits to any zero-carbon resource and give the flexibility for project developers to choose across a couple different options that best fits their particular needs. I think one unique feature there is that those credits stay in place until the power sector reaches 25% of its 2022 levels. There's also consumer-facing credits as well that are designed to encourage the deployment of things like electric vehicles, heat pumps, and other end-use technologies.
Jesse, what can you add to that?
Yeah, I would just say the way I typically describe it to people is it's putting clean energy on sale for Americans, right? We're all familiar with when you get a discount on things at the grocery store or at Amazon or wherever else. That's effectively what the Inflation Reduction Act is trying to do. It's using the purse strings of the federal government through a series of tax credits, grants, rebates, loan guarantees, and other financial incentives to put Uncle Sam's thumb on the scale, on the clean side of the ledger, and make adoption of all those clean energy technologies cheaper and easier. And the goal is basically to make it a better financial decision for households or businesses or utilities or others to transition towards lower carbon technologies, rather than have to do it out of the goodness of your heart. We're trying to kind of shift the financial calculus for everyone, and that's really the kind of impact that it's having across the board, and to varying degrees and varying incentive levels in each of the sectors. And it really, in my view, puts for the first time the full financial might of the federal government behind the clean energy transition, right? It's really lined up, providing a strong tailwind across all sectors in a way that we really have never had before.
Now, late last year, the two of you collaborated with a number of other scientists on a study that was published in Science magazine called Emissions and Energy Impacts of the Inflation Reduction Act. Can you describe the article, John, and particularly maybe why energy and climate modeling was such an important component of that study, and what the impact of that on potential emissions and energy system impacts?
Sure thing. IRA is pretty complex and covers such a wide breadth of the energy system that makes the sort of modeling and analysis that Jesse and I alluded to earlier really important for understanding its potential impacts. Because even though it sets up these incentives, actual uptake depends on a host of factors, whether it's consumer uptake, the relative cost of technologies, interactions with other local, state, and federal policies. And so after IRA was passed, we formed this IRA modeling collaborative, both to help to advance the modeling and data needs from the modeling community, but also to bring together modelers from about 17 different organizations, universities, consultants, academia, nonprofits. And I guess my experience has been that in the past, whenever a new policy is proposed or enacted, there's a flurry of studies that are released, and decision makers really want to understand where studies agree, where they disagree, and why. And so with that background, we brought this group together to help to compare on an apples to apples basis emissions and energy system impacts of IRA. And what resulted from that was the science paper.
Jesse, what can you add to that?
Yeah, I think that's a good description of why this kind of modeling is so important. The Inflation Reduction Act is not one policy intervention, it's dozens. And it's really hard to understand, a priori, how do all those different interventions across the energy system interact with each other? For example, there's incentives for electric vehicles and heat pumps on the one hand, right? That encourages increased electricity consumption, that displaces natural gas and petroleum use or gasoline use. But the full impact of that depends on what's happening in the electricity sector as well, right? And the cost of electricity and the relative benefits of adopting an EV versus an internal combustion car depend on what's happening in the electricity sector and how affordable electricity is and all these sorts of interactions. And there's just countless interactions across the energy economy like that you need modeling tools to help us understand. And it isn't to say our models are perfect at predicting what the future is going to look like. If it was, I think John and I would be off, making billions of dollars predicting the future. But what it does do is help us kind of create internally consistent ways to represent these complex systems and, start turning knobs and see what happens if I move something over here to the other sides of the system. And they're really helpful as decision support tools to get a sense of where, the aggregate impact of these policies is going to land us and where they might fall short. Where are the greatest emissions reductions likely to come from? How might that impact the cost of energy for households or businesses? These things that people really care about. I think of it a little bit like the role that the Congressional Budget Office plays as federal policy is being debated. When you have all these different measures all added up in one bill, senators and congressmen and their representatives want to know, how much is this all going to cost the American people, or how much is it going to raise in terms of revenue from these different tax provisions? And the folks at the CBO, the Congressional Budget Office, use a variety of different modeling tools and forecasting tools to try to give people an aggregate picture of what the budgetary impact of these laws is. And here we have a set of energy and environmental goals and economic transformation goals. And what our models can do is help us understand similarly what the aggregate impact is on our energy system and on our environmental outcomes like air pollution and environmental justice and the cost of electricity.
I'm just curious because again, I'm not an expert, but can you, give a simple sort of explanation of what modeling is?
It's looking beautiful in front of the camera. No, not that kind of modeling. Yeah, so these are basically mathematical representations of the most important, I would say, constraints on how the engineering and physics of our power systems and our energy systems work, and the kind of economic incentives or balances that markets deliver. So, supply has to equal demand. You can't just have, goods magically appear or magically disappear, right? We have to have certain balances in the economy. Physics has to be balanced. Electricity, production has to go somewhere, right? And so we can basically create mathematical representations, simplifications, but representations of those kinds of interactions of both technology and engineering and physics, but also economics and policy incentives and constraints. And use those to represent how energy systems behave at a large scale. And those are handy because once you've built one like that, I can say, well, what happens if I say make electric vehicles $7,500 cheaper, or give a $28 per megawatt hour production tax credit to wind and solar farms, which are the types of provisions that we see in the Inflation Reduction Act.
And yeah, I would add to that I think one benefit of a multi-model study like ours is that there's so many inherent uncertainties about those physical systems and the way that they'll evolve, the social systems that are embedded within those. And I think you can view multi-model studies like ours sort of like hurricane tracks, which show a range of pathways that a storm might take. And likewise, model intercomparisons give different possibilities for those emissions outcomes, those energy system outcomes. And just like you shouldn't prepare for a hurricane by ignoring many trajectories and just focusing on one, it's valuable for decarbonization planning to consider a range of different outcomes as well. Again, because there's typically more uncertainty about the social systems compared to physical ones.
I think that's a really good point, John. And the way I describe that to my students is sort of structural uncertainty in these models, which is basically, you have a representation of the world in this model, but they're all abstractions. And so there are different ways that you could create that abstraction. And John's model might look a little bit different from my model, which looks a little bit different from another model. And so that's sort of at the core kind of mathematics of how we represent the sort of physics of the world and the economics. But when it comes to modeling policy, and particularly in this case of the Inflation Reduction Act, there's also a little bit of an element of professional judgment that each of the modeling teams has to make in order to translate a piece of legislation into an implementation in our model. And sometimes that's very straightforward, right? Like the law just says, all right, this technology gets this much cheaper or this much more expensive or something like that. But a lot of times it's a lot more subtle than that. We have to think about, okay, well, I've made EVs $7,500 cheaper, but what does it actually do to consumer adoption, right? And how do I represent that in my model? Consumers are not perfect, rational, cost minimizing agents the way that maybe some economists might think. Like, there's all kinds of other considerations, and cost is not the only thing we care about in our vehicles. Right? There's a whole basket of attributes that we care about when we're thinking about what to buy. And so you can't just sort of place that economic incentive in and say, that's all I need to represent. Like, there's a bunch of complicated things there. And I think each of our modeling groups approach that in slightly different ways. And so again, having a comparison, not just of different models of the energy system, but also different modeling teams' judgments and implementations of how to translate from this complicated several thousand, page long piece of legislation into a particular modeling scenario to represent that is also really valuable.
John, did you look at how maybe power sector investments may change because of this bill, or particularly maybe with the investment in and deployment of emerging technologies? And then two, wondering about maybe looking at, for us, for consumers, I mean, how is this going to, or how did your model show how this could impact household energy bills?
Yeah, excellent questions. And I would say that despite the differences in the models, I think one theme across the 11 models that participated in the study is that IRA may be a really large influence on power system investments and on emissions over time. And so one of the things we see IRA doing is amplifying this trend we've seen in recent years of increasing wind, solar, and energy storage deployment. I think across the models, we see something like 2 to 4 times increase relative to a case without IRA incentives. And that's much larger than even historically the single largest wind and solar deployment years. That's almost each and every year on average between now and 2035. There are some differences across models in how quickly you might see some of those changes. And that reflects the fact that many of these near-term bottlenecks, whether that's ramping up supply chains or navigating the interconnection queue process, or even thinking about financing and interest rates, there is differences across models in terms of how quickly those dynamics might change. But in addition to wind, solar, and storage deployment, we also see IRA impacting existing nuclear. There are credits for keeping those units online. So we see more nuclear over time. It's existing. But we also see some CCS addition for coal and gas plants. There's a lot more variation across models, given the uncertainties about ramping up those emerging technologies. But I would say that that's something that many of the models that are participating in the study saw.
And CCS is carbon capture.
That's right, carbon capture and storage. And that can be retrofits of existing plants, or it could be new plants with CCS. But there's, these incentives within IRA are not just for the power sector. There's also carbon capture and storage incentives that could apply for direct air capture, basically pulling CO2 out of the atmosphere, as well as carbon capture for industry and for fuels. We do see some models that have that deploy CCS for those non-power applications.
I think it's fair to say, John, and you correct me if I'm wrong here, that across all the models, the bulk of the emissions reductions that we expect to see over the next decade or so, kind of the first decade of impact from the law, come from accelerating a couple of trends that are sort of already underway, but get supercharged by the law. And that's the growth of wind and solar power, which also accelerates the retirement and reduction of coal-fired generation in the power sector, and the growth of electric vehicles, which help us reduce the reliance on petroleum-based transportation fuels. And of course, the cleaner the grid mix gets, the more beneficial that transition to EVs also is from an emissions perspective.
Yeah, that's exactly right. And the majority of emissions reductions, at least through 2030, seem to come from the power sector across the models. I think the specific numbers are something between 40 to 80% of reductions come from the power sector. But as you get further out in time, you increasingly have contributions from these other sectors as well. And as you mentioned, Jesse, transport is a big one, both in terms of current emissions and in the potential for mitigation moving forward. Many of the models suggest that by 2030, 2035, you have over half of all new vehicles sold are cars with a plug. But it's not just passenger vehicles, it's also commercial vans and trucks and buses, where there are also incentives through IRA. And again, that's kind of amplifying, this trend that we're already seeing. I think something like almost 10% of new vehicles last year, passenger vehicles, were EVs of some sort. So yeah, IRA is basically supercharging these existing trends.
Let me just ask, because the IRA is just so far-reaching in so many different ways. But what about from sort of from both a policy-related standpoint and then a market-related standpoint? What are maybe some either changes or some things that we'll be seeing or how in the future in those two areas, and how IRA impacts those two areas?
Yeah, so IRA itself can change trajectories from the policy and market side, but also developments there independent of IRA may change how impactful IRA is over time. I think one example on the policy front are state policies like renewable portfolio standards, or at the federal level, thinking of different regulations. One in particular that we modeled recently in a white paper was looking at EPA's proposed power plant rules. And those were proposed last year, likely going to be finalized sometime this year. But those rules are based in part on the application of technologies like carbon capture and hydrogen, which are both subsidized through IRA. And so our analysis suggests that the impact of those rules depends on the costs of those technologies moving forward, what you assume about fuel prices, whether gas prices are low or high. And those are pretty important uncertainties when you're thinking about IRA and sort of general trajectory of especially the power sector, but also broader energy systems.
Yeah, I think that potential to spur additional state level action is a really important dynamic, in addition to the ability to give EPA and DOE and other regulatory agencies a bit more fortitude to enact maybe a little more stringent regulations than they would otherwise, since IRA basically subsidizes the cost of compliance. We've also seen a whole number of states since the passage of the IRA redouble their commitments to electric vehicle transitions in both light duty vehicles and also commercial vehicles, following California's lead in the advanced clean cars and advanced clean trucks rules. I think there's now something like 14 or 15 states that are following in that direction, and it represents over a third of the light duty vehicle market in the United States. So, that's been a major accelerant. It's a lot easier for a state like New Jersey, where I'm from, to commit to that goal if we know that, the federal government's picking up part of the tab for New Jersey auto buyers, right? And the same is true for these renewable portfolio standards or clean electricity standards, with more and more states across the country committing to transition to 100% carbon-free electricity by a certain date forward. In New Jersey, we haven't yet enacted this in statute, but the Governor Murphy, had an executive order in 2018 or 19, before the passage of the Inflation Reduction Act, that set the goal for the state to get to 100% carbon-free electricity by 2050. My group, the Zero Lab at Princeton, did a study after the Inflation Reduction Act passed that found that we could likely hit that goal by 2035 rather than 2050, while paying the same or likely less than we do today for bulk electricity supply costs, thanks to the fact that the Inflation Reduction Act, again, is going to lower the cost of all of these clean energy technologies for New Jersey electricity customers. And after our study was released, the governor accelerated his executive order last year to 100% clean electricity by 2035. And there's legislation in the state legislature here in New Jersey to enact that goal in statute. And so that's just one of many examples. Michigan, Minnesota, others around the country have all have been increasing their ambition because basically whatever level of action made political and economic sense prior to the passage of the Inflation Reduction Act, now the fact that Uncle Sam is picking up 30% or 50% of the tab means that states can go further and faster. And that is really important because we haven't talked about this yet. Despite the accelerated emissions reductions that the Inflation Reduction Act delivers, we're not on track yet to meet our national climate goals. So these state commitments, these follow-on regulatory actions are all really important. And the fact that the IRA makes clean energy actions cheaper makes it much more likely that we're going to see those actions going forward. And that's not something reflected in any of our modeling. We're not trying to predict those follow-on effects in the modeling presented in this paper and other works. We're just trying to say what happens under current policy. And so I'm optimistic that further policy actions will help close some of those gaps and make additional progress.
I just can't tell you how really interesting you've made what I would assume might have been a really difficult topic for a lot of our listeners. So I really appreciate John and Jesse, both of you, for coming on today. For our listeners and viewers, if you want to learn more, we'll have some links either in the bottom of the video or on our webpage in the description for this episode. So again, John and Jesse, thank you again so much for joining us today for this episode of EPRI Current. Again, I'm your host, Bill Florence, and we'll talk to you soon. If you like today's show, we invite you to subscribe to our podcast. And feel free to share the podcast with your colleagues and friends. For more information about EPRI, please visit our website at www.epri.com. And don't forget to follow us on LinkedIn and Twitter at EPRI News. Together, we are shaping the future of energy.